Good morning, everyone, and welcome to week 11. Now, by this point, you're probably getting quite used to our regular little history interludes. So today we have Andrew Yao, who was born in 1946 in Shanghai and is still around and kicking. One cool thing about him is he has both a PhD in physics and a PhD in computer science. From his computer science PhD is from UIUC, and his physics PhD is from Harvard. He is responsible for a number of things, including the theory of random numbers, which I know Harwin was particularly interested in. And as well, he's also responsible for the Dolev-Yao security formalism, which models different types of computer security as games between an adversary and a defender. And the way the formalism works is if the adversary can get some extra information that the defender is trying to prevent, then it proves that the given thing that you're trying to model formally is insecure. Now, one interesting fact about Andrew Yao is he lived in America for most of his adult life until in 2015 when he renounced his US citizenship and returned to China with another prominent Nobel Prize winner, Tang Ning. So, I forgot to mention, Andrew Yao did win, of course, win a Turing Award like many of our other, the people that we present. And now he is the Institute Dean at Tsinghua University and also a distinguished professor at the Chinese University at Hong Kong. So another really key figure, and as well, an interesting individual who contributed substantially from China's perspective. So today's lecture is one of my favorite ones because we get to talk about a topic that is very near and dear to my heart, and that is music, and also, in this case, musical theater. Now, unbeknownst to all of you, there is also someone else in the audience here who enjoys musical theater, and we discovered this last night at Hadestown. So yes, that is Danny right there, and we are at Hadestown, where I had an opportunity to enjoy the show last night and also go backstage. If any of you have the opportunity before they leave on, I think, July the 19th, please go. It is a wonderful show. But unfortunately, during the show, there was a lot of interesting, complex music, and I was left with a bit of a question. There was this one interesting piece, and I wanted to know what note Orpheus was playing on the lyre. It sounded like some kind of combination of notes, potentially, and I want to know, could I use a computer and maybe a recording of this to figure out what notes were being played? So one thing I could do is check the recording. Does anyone here have perfect pitch? No? We do? You don't need to have perfect pitch, that's true, but that would be probably the fastest way of identifying what note someone was playing if you did have perfect pitch. But before we even get to that point, if we don't have someone with perfect pitch in the audience, we're probably going to need to store the music somehow, put it on the computer, and then run an algorithm on it. But, I mean, nothing we've learned so far in class tells us how we can actually store the music. So does anyone have a clue or a thought of how we might take something that we hear and encode it into a representation that we might be able to store and algorithmically manipulate? How would you store a sound? Any takers? Okay, Mal, you're closer this morning, so we'll go with you. Oh. It's on.
Well, I think that since, we do have techniques like records to, store the sound in a kind of wave pattern. So I think that maybe we could store the music also in a wave pattern, but basically it was digital on computers, yeah.
Okay, wave pattern is one interesting idea. Gav?
Maybe each each of the pitches at each time interval could be represented by like a certain frequency, and if you have a different array of different frequencies, then that could possibly represent the sound.
So these two ideas have something in common, and that's that they both refer to waves, which, whether you're talking about frequencies or waves, they're both part of the same physical notion. And what both of these people are referring to is what the air is doing when it vibrates and actually causes our ear to perceive sound. So this is vibrating molecules in the air that move up and down when someone makes noise, when I speak, or when Orpheus plays the lyre. And it vibrates, and those vibrations travel to our eardrum. Our eardrum vibrates. That triggers electrical impulses down a nerve, and that nerve goes to our brain, and we perceive the sound. But at the end of the day, what we're getting is vibrating air molecules vibrating at different rates and at different amplitudes. So one thing that we could do is we could measure how fast the molecules of air are moving at different time intervals, and then use the rate at which they're moving to then create what we in mathematics would see as a wave, but which ultimately is a physical phenomenon, which is individual discrete air molecules moving. There's no wave per se in the air. The wave is more a mathematical abstraction that we use to model the way that the molecules vibrate. So if a molecule vibrates persistently at a certain speed up and down, that molecule would be moving in a way that we could model as a wave. Or if we have a group of air molecules moving, we could also model that as a wave, as they all tend to pass energy from one to the other. And you could imagine that pattern of what looks like a wave going across the different air molecules. So instead of how fast the molecules are moving at time intervals delta t, we could also measure how high they're going, and this is the amplitude of the wave, and this is what you would perceive in your ear as the volume. So the rate at which they're moving is going to be the frequency, which gives rise to different pitches, so high or low, and then how much they move is going to be the amplitude. Now, because again that we're talking about individual air molecules, and we're talking about time frames. Now, time is continuous, so this is going to be difficult for us to put in on the computer. How do you put in what's happening at every single moment in time? That's not really possible. What could we do alternatively to still give us the perception of sound, or at least having stored the sound? Garv, you can go again.
Possibly try to interpolate between the values.
Yeah, that's exactly what we're going to do. So instead of actually having every possible moment of time encoded in our computer, what we're instead going to do is choose some rate at which we will measure the molecules and measure what's happening in our wave, and then we will plot on our plot what happened at that particular point. And as long as we do it with fine enough granularity, our ears won't be able to tell the difference between what is actually stored on the computer and what happened in the real world originally. To the extent that when you then play it back, the waves that come out of the speaker will very closely match the original waves that were passing through the air at the time that you recorded it. So this is what Orpheus might have been playing. Does anyone know what this would sound like? Anyone have an idea? It's a bit low. It'd be higher than that. Would not be. Okay, I will play for you. Here we go. That is actually the sound that makes. Does anyone know what that's called? Vincent?
Is it the A440?
It is indeed A440, which if you're running a concert orchestra, that is the standard frequency that you're kind of meant to tune around. Now, of course, it sounds a little unpleasant, and that's because the wave is kind of a perfect 440 hertz wave, and in real life, instruments actually have slightly different looking waves that are combinations of different things that are shaped by their materials and what they're made out of. And the way that they're structured and how large they are, etc. But if we are abstracting this out a little bit, let's forget for the minute that real instruments don't make a perfect sine wave. Certainly last night, Orpheus sounded a lot more beautiful than that buzzing noise. But if we were to go over to our piano, this would just be the note above middle C, that A over there, which we try and tune at roughly 440 hertz. As close as we can get as possible, noting that the waveform of the piano is going to look slightly different because it's a piano and not a sine wave generator. Now, unfortunately for us, the wave that was played last night looked a little bit more complicated, and this is probably because it was the combination of multiple notes. And so the big task for us in the first section of today's lecture is going to be to try and figure out a way that that we can represent all of the values at each of these points. And then we'll talk a little bit about how you might actually decompose this into the different notes that were actually being played in order to produce this wave. Now, one other thing I will note about this one is if we wanted to figure out the frequency of the wave, we've got a relatively easy way of doing it. Just count the distance between the peaks, which looks to be, if you eyeball it, it's about 0.0022-ish, and divide 1 by 0.0022, and you get approximately 440. I think it's 440.5. If you measured it perfectly, you'd of course get a better answer. So we can do the same thing here and try and compute the values for each point, try and compute the peaks between, the distance between the peaks. But because this is a combination of multiple different notes, we're not going to be able to work that out quite so easily because we can't tell what sine waves went into this to make up the picture. So that's going to be our task. And one challenge with what we're seeing here is that there are also very different amplitudes. Some of the waves, some of the notes might have been a bit louder, some of the notes might have been a bit softer, and either way, we've got values to represent, some of which are spaced very far apart, and some of which are spaced very close together, and the ones there are a whole lot in the middle, but then there's also a whole bunch of points clustered at the top. So whatever way we're storing these in the computer, if we want it to be efficient, needs to be a good method that can store values that are substantially different in range and yet at the same time gives us adequate precision such that we can distinguish between the small differences in those values at the top, which are very large, while at the same time storing the values that are very small, very close to zero, that are also kind of spaced closely together. So what tools do we have in our numeric toolbox in C that we could use to potentially store these? And we'll go with someone different.
Yeah, could we just store each value, each amplitude value, and each discrete time interval in a separate axis, and then they correspond to, so we can model that graph?
And what would the type of values be?
Would they be a float?
So why did you pick a float and not an integer?
Because integers, each variable is a continuous, so they can't be limited to just whole numbers.
So how many decimal places can you store in a float or a double?
Was it something to do with 32?
Something to do with 32, and the answer is it's kind of a trick question, and we will explain that a little bit soon. But there's a limit, right? And so why would we then use floats rather than integers?
Because that,
It's a tricky question. So we'll pause for a second and we'll come back to you. Okay, so there are a few things that we want to do with our numbers, with our storage, such that we can store the numbers. So we want our numbers to be correct when we do a mathematical operation on them, although what that means might vary, knowing that we have limited precision in our computer. We want the operations on the numbers to be efficient. So if you add two numbers together, you don't want to have to do all these different calculations that are difficult and slow in order to make that happen. We want it to be reasonably easy to implement the numbers in hardware or in software. We want it to be effective. So in this case, we're talking about storing music, and so that has a number of different features that we've seen. We need big numbers and small numbers and numbers that are very close together. So that's going to be our effective. And then also some other things that might be good is we want it to be predictable in its bit representation, so that if you look at what the computer's doing under the hood, it's easy to understand as a person what it's doing. That might be desirable. And then we also might want to be able to scale to arbitrary precision. So if we need more numbers after the decimal point, or we want to store more digits of it, we might want to be able to do that depending on the task at hand. So let's say we're, again, going to our music task. How would you use integers for this task if you really wanted to?
Wouldn't that involve some level of scaling?
So that is exactly correct. You use integers and then you can multiply by a fixed amount such that you can represent the size of the number. Now what's the problem that we're going to have here for our music? If we multiply by a fixed amount, if we scale all the numbers up so that we can represent the really big numbers.
Would it, if it's scaled by a constant, would not all be scaled by the same value
And the problem is,
that we need to find?
not that we need to find all those values, but we've got both really big values and really small ones. And so our scaling might end up actually cutting out our ability to model both the really big numbers and the small numbers, because we've only got 32 bits to represent numbers. So if our smallest number is multiplied by whatever it is, whatever our scaling factor is in order to represent the really big numbers, we're going to run out of bits. So it doesn't work if we multiply them by a fixed amount. What's another way that we could do this instead of multiplying every number by the same amount?
Multiply each by a different amount?
Okay, and how would you do this mechanically in C? Let's say you can write a whole program to do it.
Could you store, you can create another array with that scaling factor corresponding to each time point?
Ooh, that's exactly what it says. We could instead keep track of the integer or the numbers that we have, along with a second array that indicates for each number how much to scale it by. And those two numbers together would represent the actual value of the whole number. Now let's say that I have blocked you from using a second array, but you can manipulate the bits however you like of each individual value that you're storing. Can you think of a way to achieve the same effect? I've given you 32 bits. You can use them however you like, but you want to achieve the same thing.
Could you in some way separate that 32-bit into value and scaling factor?
You're doing very well today. You're getting everything right, one in a row. So instead what we can do is we can still use integers, normal values that our computer is able to represent, but somehow we can divide up the bit pattern inside that number such that some component will represent the number, some portion of the bits will represent the value, and some portion will represent the scaling factor. And if we're being clever as well, how could we do represent negative numbers?
Sorry, trying to think back.
So you can arrange the bit pattern however you like.
Well, you can add that third component to indicate whether it's positive.
So we could add another component indicating the sign. And we'll talk about, for regular integers, other potential choices for how we might do this later in today's lecture. And so this discussion about what is the right way to represent numbers in our computer's memory is actually part of a discussion around two different types of representations of numbers that have decimals in them, known as fixed point, where you have the decimal place is always in the same point in the number, and you multiply by a fixed factor, or you alternately have portions of the number in two different arrays, or what we call floating point, which is where we're going to, for each number, allow the decimal point to move around based on how much we're scaling it by. So just as we can scale out fractional numbers by multiplying them by some amount, so 0.5, if you multiply it by 10, it's no longer a number with a decimal point, it's a 5 that you know to scale back one place. So divide 5 by 10 and you get back to 0.5. So for any number with a decimal place, we can turn it into an integer just by multiplying it by enough, given that in the computer world, we're always dealing with limited precision. So for In maths, we can't do this because it's not always the case that you can multiply a real number by some scaling factor and get an integer. That does not work. But in the computer world, when we're dealing with trying to store numbers with decimal points in them, this is a trick that we can use. Now, you might ask, is there a way to represent numbers with infinite precision? And the answer to that is no. Our computers are finite and numbers are potentially infinite. But what we can do is if we want to store a number to some arbitrary precision, we can still do that. Now, why might we choose one or the other of these? So for fixed point, it's really useful where you have a very tight accuracy target, so you know exactly that you need to be very, very accurate, but you only need to be accurate within a certain fixed range. So if you're storing numbers that are between 10 to the negative 1 and 10 to the negative 3, and you know that that's going to be your range, you might actually use fixed point. You might not store it in floats, you might store it in the equivalent of integers and just do that scaling thing. And the reason is that integer addition and subtraction is very, very efficient. The way that we store integers in memory is fairly easy to introspect, and it's easy and fast to implement in hardware. Another place you might use this is if you're doing cryptography or if you're in an environment where there are real-time deadlines. So you know that the calculation always needs to be done in a tenth of a second because the result of the calculation is being used for your plane's control systems. And so having these very narrow tolerances is a reason that we might want to use fixed point arithmetic. For floating point arithmetic, like we saw with the music example, it's going to be very, very effective where we need to store numbers in a much wider range and where we're going to want precision in that range to be better. So for an example, if you want to be able to store both the notes that are the very loudest and at the very both at the very loudest, and you still want to be able to make distinctions between the loudness of those points, and also when something is really, really soft, you also want to be able to distinguish between different levels of softness. That's when you might use a floating point number. And if you actually look at the most modern, like my little sound recorder over there, that's actually using 32-bit floating numbers to actually store my vocals from today in order so that no matter how loud I get or how soft I get, it'll actually still come up okay in the recording. And that would not be possible using other different numeric representations. Indeed, if I'd chosen a cheaper sound recorder, it wouldn't have done that. So if I got really loud all of a sudden, or really quiet, it wouldn't have been pleasant to listen to. So hopefully for those of you revisiting the recording later, that will actually be tolerable for your ears. So where are different places in the real world where we might use fixed versus floating point? For fixed point finance, you do not want the precision of your bank account to be dependent on the amount of money you have stored in it. You want it to be just as accurate if you have $1.50 as if you have $150 million and 50 cents. You want the precision to be there all along the range of the values that you store. And we also know that at least for regular humans, our bank balances are likely to lie somewhere between negative $50 and hopefully no one here has negative $50, but on the lower end, and then on the upper end, something more along the lines of hundreds of billions of dollars if you are Elon Musk or Apple. But that's still a relatively limited range, and we don't need arbitrary decimal points. People are generally happy with their finances to 2 decimal points, or the banks might store it to 4, something like that. Cryptography is also where we'll use fixed point systems, car systems, and then also in image and audio decoding, we'll often use fixed point in many different circumstances, although for audio, the world is increasingly moving to 32-bit float. So floating points get used substantially when you're doing music editing, music production. You'll work in floating point, astronomy and particle physics, 3D graphics. And then the last one, and this is where it becomes super, super relevant, is for machine learning. We actually use floating point because the accuracy of the parameters in a machine learning model don't matter that much to the nth decimal place. You can cut them off at a certain decimal place and still get a good model. Now, this is actually kind of interesting because I was planning on throwing out floating point from the curriculum about 2 years ago. And I thought, most stuff that we're going to care about is going to use fixed point integers. And then, of course, there was the giant explosion in neural networks and machine learning techniques, so I decided we would keep it in. So now let's go to Alex's proposed scheme, and he was right on the money here for how we're going to represent floating point numbers, which we will discuss for a little bit now so that you actually know how it works under the hood. So just like Alex said, we're going to have some portion of the number that is going to be used for what we call the mantissa, which is storing like the value. We're going to have the exponent, which is how much we're going to scale it by. And then the base, which we're always going to set to 2 because we work in binary, and so we're always going to scale in powers of 2. And then our exponent e is going to tell us how many powers of 2 should we scale it by. And then out the front, we'll have 1 bit that we use for the sign of the number, whether it is a positive or a negative number. So let's do this with a real example. Here is storage of a number, 5.432 to the 3. So let's put that in. 0.432 to the 3, and that is reading out the digits, negative 160.27998158. Now you might notice that I only have 4 figures in my mantissa here. I have 5432, but when I read out the results, I read it out to like 8 decimal places after. And this tells you something important about what this representation is going to do. It might not actually be accurate to all those decimal places that I read out because of the way that our scaling interacts with the mantissa. And so this is why we might want to use a double, which is going to give us more bits that we can potentially use for the mantissa than might be used for a float. Because the less bits you have in the mantissa, the less accurate you're going to be able to be when representing the overall number. And then just as a bit of terminology, we're going to call this 2 to the 3 combined the characteristic of the number. So instead of scaling, we'll call it characteristic. But now we have a bit of a question. So Alex told us to split the number somehow into the bits for the characteristic and the bits for the mantissa, but he didn't tell us how to divide the number, how many bits to use for each. Do you have a view on that? So what would happen if you gave more bits for the characteristic and fewer bits for the mantissa?
It would be less accurate.
Less accurate, but what do we get in return?
More decimal, no. Oh yeah, a wider range of values.
A wider range, yes. So the more bits we have for the characteristic, the greater the scale of values that we can represent, but we lose accuracy. So how much should we do? How much accuracy should we have? How much range should we have?
I guess it depends on the application.
Yeah, that is the right answer, is that it depends what the actual right amount here is. However, most people, when using numbers on their computer, don't want to have to think about, okay, how accurate do I need this number to be, and and what is the range of numbers that I'm going to need to represent with this representation. And so what we have instead is we have what are called standards, which are agreed upon international settings for these values that we're going to use. And for a float, this is going to give us roughly 24 bits in the mantissa, and for the double, roughly 53 bits in the mantissa. And the standard that we're going to be talking about today is called IEEE 754. IEEE is an international organization for electrical engineers, but they also standardize a number of things to do with computer science, particularly at the boundary of computer science and electrical engineering, which is where things like hardware design and integer representations do come in. Now, one note here is that the integer representation that we're using in class is different from the book, only very subtly, because we're going to introduce an element of the representation called the bias. So if you go into the book, it is going to be ever so slightly different, just so you're aware of that. For purposes of assessment, we will tell you which we're going to use, so you should be familiar with both. The book one just leaves out one step, so it's actually easier. So the way we actually go about doing this for IEEE 754 is the following. Now, you don't have to have these steps memorized in this particular format, and also once you've practiced a few times, it becomes relatively straightforward. So the first is write out the number in binary, and we'll talk about how to do that a little more in a second. The next thing you do is write the number such that only one digit is to the left of the decimal point and multiplied by a power of 2. Encode each significant figure in the mantissa. So this is where we're going to be writing the value out. So write that out in the mantissa. And then add a bit for the sign where 1 is for negative, 0 is for positive. And then for the exponent, you're going to figure out the exponent as 127 plus what the value would otherwise have been. So if the exponent would be 127, to write that out in the exponent space, which is going to be those pink boxes over there. If your exponent is actually 127, you fill that with zeros. If it's 128, you would put a 1 in there. And this is just a component of the IEEE 754 standard. Okay, so the first thing we have to do in order to actually operationalize this, which is a little complicated, is to figure out how to write numbers in binary. And we have already done this a little bit, but let's just do a demo again to refresh your memory. Okay, so let's start out just by writing the number
1 second.
14 in binary. So who thinks they already have an idea of how we might go about doing this?
I think we need 4 bits since it is, under 16.
So the first thing to do is figure out the width of the integer, of the bits available to us that we're going to store. So in the case of a 32-bit integer, we'd have 32 bits available, but Ronald is right, we're only going to need 4 bits for this because it is under 2 to the... It's underneath 2 to the 4, and so being smaller than 2 to the 4 means we need 4 bits to represent it at most. Okay, so go ahead. What's the strategy going to be?
Well, I guess since it's not... Oh my god. I think we fill out the last bit, the one representing 8.
So here we have our 4 bits of the number, 0 indexing them.
Oh, yeah.
So starting, if we were to write what each of them represent, this is going to be our bit for whether, for the ones place, just like in high school arithmetic, how you have the ones place, and then the tens place, and then the hundreds place. Binary is going to work the same way, except instead of ones, tens, hundreds, thousands, we're going to have the ones place, the twos place, the fours place, the eighths place, and the 16ths place, although we're not going to use that because we're not going to need it. Okay, so you say start with which place?
We start with the largest place, so we put 1 on the 8.
So what's the question that you ask yourself in order to determine whether to put a 1 or a 0 in that place?
It's less than the number.
So what we're actually going to do is we're going to take 14 divided by 8, and what do we get?
It's like 1 point something.
So the other way that we could do this is using remainder mathematics. So what we could do is figure out, okay, if we divide 14 by 2, we get
7.
7. So, and what remainder? 0. Okay, so let's put a 1 in there, 1 in that place, and no remainder. To write 14 in binary, we're going to use repeated division by 2. So each division is going to ask how many full groups of 2 can I make out of the groups, and if there is 1 left over. The leftover, which is the remainder, is going to tell us if we need to include the current power of 2. So to think about it, think of it like grouping objects. Start with 14 objects, say oranges, and first we're going to ask how many pairs of oranges can I make. So 14 divided by 2 is 7 pairs with no leftover with no leftover oranges. So the first place is 0. We have an even number of oranges. Okay, now we have 7 pairs of oranges. Can we group those pairs into pairs? So 7 divided by 2 equals 3 groups of pairs and 1 pair left over. Because we've got 1 pair left over, that means we've got 2 spare. So that means we have an unmatched group of 2. So we put a 1 in the 2's place. Okay, now we've got 3 groups of the 4s. So divide again by 2. It gives us 1 group, remainder 1. So that gives us the 4's place because there's a leftover group of 4s. And 1 divided by 2 equals 0, so remainder 1, and that's the 8th place. So we weren't able to pair any of the group of 8 oranges with another group of 8 oranges, so we had a group of 8 oranges left over, and that's our remainder, and that puts a 1 in the final place. So what we're doing here is each step we're grouping into bigger powers of 2, so 1s, 2s, then 4s, then 8s, and the remainder is going to tell us if that power is needed because there's a leftover group of that size, and then the quotient is going to become the next input. So our procedure overall is divide by 2, write down the remainder, divide the quotient by 2 again, and keep going until you hit 0, and then read off the numbers. So for 14, that gives 1110. So in binary, it's 1110. So now we have 8 plus
8 plus 4 plus 2.
8 plus 4 plus 2 plus 0. We get 14. So hopefully all of you are capable of doing that grade school addition, but let's look at the way this actually worked. So we did 8. In the 8th place, we have a 1. So we do 8 times 1. In the 4's place, we have a 1 as well, so plus 4 times 1. The 2's place, we have a 2 times 1. And the 1's place, we have a 0 plus 1 times 0. That gives us our number there. So the basic idea here is to do repeated division by 2, figure out the remainder, and use that to calculate whether you put a 1 or a 0 in each of those places. But because we're starting from the 8th place first, from the largest place first, what we call the most significant bit, we are going to write our numbers down kind of in reverse order. So that was 1, 1, 1, 0, rather than other way would be 1, 1, 1, 0. Okay, so that's good enough to represent 14 alone. But now let's try represent a number with a decimal place in it, such that we're actually going to need to do the scaling, and we're going to use our floating point IEEE 754 standard. So we already know how to write 14. So Ronald told us that that was 1, 1, 1, 0. But now we've got the issue with the fractional part. So we're going to now use a slightly different process to represent our fractional part and figure out how to actually convert that into binary. So to convert the fractional part into binary, we're going to use the following procedure. So the first thing to do is to multiply the whole fractional number by 2, the entire number, then figure out the digit at the front and the remainder of the number after that. You're going to add that leading digit to the final number that we're going to write down to our final bit representation, and then just keep repeating the process until you end up with 0. Start with a very, very, very easy example. And this is the number 0.5 from our 14.5. So the process is the first thing we do is multiply the fractional number by 2. So some help here. It's 1. That gives us 1.0. Now separate out the leading digit, which is 1. Write that in our representation. And then if there is any remainder, then we would repeat the process, but there is no remainder. So we just write this as 1. So if we go back, we're going to have a 1 here. Now what we need to do in order to complete our representation here is we're going to need to follow the rule that the decimal point should be right next to only the first meaningful digit. So if there were zeros there, it wouldn't matter. But we're going to want to move the decimal place 1, 2, 3 places along. So that is going to give us a representation of our number. Instead of writing this down directly in the mantissa, we can assume that the first digit is always going to be a 1 unless it's all set, unless the number is 0 overall. Or even if it's 0, it's going to be set to 1, and we'll see why in a minute. Which means when I'm writing it down, I don't actually include that 1 over there. I'm only going to include the other bits, because that actually saves us 1 bit, because our rule was that the very first bit of the mantissa should be a 1 to indicate significance there. So what we've done is we've taken these bits and directly transcribed them. And now what we need to do is indicate how many decimal places we shifted the decimal point. So we shifted it 3 decimal places in this case. So 2 to the 3. But now we're going to need to do our encoding such that we respect the float convention, which is that we need to write 127 plus 3 into our exponent. So what's 127 minus 3? 124. And how do we write
130.
in binary? And that gives us our representation that we are now going to put into the exponent. That is a the full details of representing the number in IEEE 754. One thing I also left out is because the number is positive, we're just going to have a 0 out the front instead of a 1 out the front. Garv, can you pass to Tim?
Testing. Okay, so 2 things. The first thing is you mentioned that we actually drop the first digit because it's going to be the same for everything in binary, right? It's always going to be a 1, except when it's 0, but you said actually even then it will still be a 1. So can you explain that? Why would a 0 have a leading 1?
So let's write that out. I shouldn't have erased this whole slide. And our sign can be 0. I don't know how many bits we're doing this with now because I've just wiped out my beautiful collection of bits. I think it's 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So that is our bias. That is our sign. And then in the mantissa,
So the 0 is encoded in the bias.
yeah. So in this case, the 0 is going to be encoded in the bias.
So when you've got a 1 in the first digit, the invisible first digit, it will get turned into a 0 by the 2 to the 0.
Would a 1 not encode to the same thing?
Sorry?
If you just had the digit 1.
Oh, yeah, then you would have a different bias because you would move the 1 to the first significant digit.
The other question I had, can I remember the other question that I had? Oh yeah, so in the top left-hand corner, you've got this illustration of the bias, right? Where you've got the arrow, you're moving it over different orders of magnitude, right?
Yeah.
So I guess what I didn't quite understand is in the example that we did, why was it moved 3? Where is it? It's moving from a basis of 0, right? 3. So that means that when we have the e as 0, it's just 2 to the 0. So in the example there where you've got like 1110.1, I'm not sure what that represented.
Say that again.
So this bit in the top left where you've got 1110.1 and you've got the arrows, what does the 1110.1 represent?
This one?
Or the other one with the arrows, but yeah.
That was 14.5.
Okay. So that's the binary representation of 14.5. And because you need to get it to the first digit, you're moving it 3. So therefore, you know it's 127 minus 3.
Yeah, so that was that's how we computed how much we were going to scale it by. And this allows us to be sure that even when we want to represent a very small number with lots of numbers after the decimal point, that we can still move it along and scale it.
I have one final question,
Yeah.
which is if you zoom out back to the number, we have our beautiful 0, okay? But what happens if I change the sign to a 1?
Then we have 0 positive and 0 negative,
That sounds
which does sound confusing. Which is one reason why why certain representations might be disfavored, because then you might end up with 2 different zeros that you have.
is in this representation, would that represent a positive 0, or would there be a special convention that represents another number to avoid that?
I think it's a different 0, but I'd have to check the 754 specification to be sure. And we'll do one more of these, actually a worked example. But you can see in each of these, what we're doing is we are multiplying each of the bits by a scaling factor still. So it's the same as if we were doing for whole numbers, where we had the 1's place, the 2's place, the 4 place, the 8 place, and the 16th place. Except when we go back on the other side, across the other side of the decimal point, we're going to do the 2 to the negative 1's place, which is the halves place, the 2 to the negative 2's place, which is the 1 on 4's place, which is equivalent to 1 on 4. The next one is 1 on 8, 1 on 16, 1 on 32. So let's actually try our process again with a different number so that this becomes a little clearer. And we're going to do the third example here of writing out 0.625 in binary. Oh. So the first step is that's showing up. Our first step is to multiply the entire thing by 2. So by 2 gives us 1.25. And now we ask ourselves, what is the integer part? The integer part is a 1. So we write down a 1 in our final number, and then the amount that's left is 0.25. Okay, now we double it again, and now we get 0.5. Is there a whole part of that number? Is there an integer? Nope. So we write down a 0, and now we do the same thing again. 0.5 by 2 equals 1. Is there a whole part? Yes. Is there a remainder? No. So we've successfully converted our number, and we have the bits 101 for 0.625. And that process, even while it looked a little convoluted, is actually fairly simple once you do it a couple of times. So I would strongly encourage you for the exam to practice just writing this out a few times. So do both the conversion to a full IEEE 754 number, but I wouldn't bother doing that to the full 32 bits because 32 bits is a lot to write out. Try doing it with a 16-bit version. Or an 8-bit version where you just specify how many bits you're going to use for the characteristic and for the mantissa. And we will tell you in an assessment if you need how many bits to use for each, if you need to write it out that way. But do practice converting integers into binary, converting fractional bits into binary, and then converting whole things into floating point numbers. Oh. What did I lose? Lost my clicker. So as a result of all our work, we now are hopefully able to store the numbers that we need in order to represent our waves and actually identify the notes that Orpheus played. But unfortunately, we still haven't actually resolved the algorithmic problem of splitting that complicated wave up into its different notes. So we know when we got that original sine wave, we could represent that, and then we could read that back out, do the calculations between the peak We could interpolate between the points, figure out what the correct equation for that sine wave is, use the equation of the sine wave to figure out its frequency, and from the frequency figure out what note that it was A. But for the complicated version, we're still not quite there yet. To actually get the frequencies, the mix of frequencies, the mix of waves that are going into it, we're going to need a pretty special algorithm. And this is why it's got a pretty background. This is the fast Fourier transform. This is non-assessable. You do not need to know how to do the fast Fourier transform for first-year algorithms, but I wanted to at least show you, because this is one of the reasons why we might care about having floating point numbers, is that it's going to allow us to use this algorithm. And essentially what this does is it's going to tell us, okay, given a wave that's some mixture of a whole bunch of different waves, like this one here, can you plot, if we were to decompose it into amounts of other types of waves, how much of those other waves are contributing to the original complicated one? So you can see here that we have contributions from a C, an E, and a G that all are combining to make up these wave patterns. So if you add roughly equal amounts of C, E, and G, you get a wave pattern that looks like this, and you'll get a Fourier transform of the wave that looks like that. So you're then able to take any given wave and say, okay, these are the different things that went into making that more complicated wave. And in fact, we could play this note as well. And I will do that for you now. There are 3 notes. Now again, that is the version as if you played it on a piano, and if you played it on a piano, the wave pattern would look a little bit differently. So I'm going to see if I can find for us a triad, a C major triad played on a signal generator. Now, as much as I would really love to spend the rest of the lecture on music theory and talk to you about overtones. Unfortunately, you're going to have to go over to South Bank for that. But feel free to meet me there sometime and we can nerd out over music theory. So on our piano, this would look as follows, just those 3 notes. And this is what we're going to call harmony, because the notes are actually going to be in the waves are going to be in nice multiples of each other. So if we go back here, we can, and we would compute the ratios between these notes, we would get nice spacings, nice integer spacings between each of the notes as multiples of each other. Now we can do what we did for our discussion about floating point representations to integer representations. And some of this is just going to be a refresher. Alex, you're in the hot seat again. So do you want to turn on your microphone? So how do we store negative numbers for integers? What are the different ways we could do it?
There was that clock.
So start with the simple one that's very close to what we just did for floating point numbers.
You just have one bit to indicate whether it's negative or positive.
So just have 1 bit to indicate whether it's negative or positive. This is called sign magnitude representation. And this is again going to have the issue that we're going to get 2 different patterns for 0, as Tim pointed out. And this is explicitly one of the reasons why we don't use sign magnitude representation, is because then you have all zeros and a 1 out the front for negative 0 and all zeros for positive 0, which is going to make our arithmetic more complicated. And we're also going to need additional hardware to deal with the fact that we have this extra bit at the front, which is going to impact how addition and subtraction work. Okay, so that's one way of doing it. What's another way of doing it?
Wasn't that that thing where it's like a clock face and you separate half and half?
So we can do half and half. And there are 2 ways of doing half and half. One way is we could say, okay, for any time that you see a 1 in the positive number, turn it into a 0, and for any time you see a 0, turn it into a 1. But that doesn't give us the nice representation that we had before, and so again, it's going to be more complicated, both in hardware and software, to actually implement. So one very slight change we can make to actually get to what you were talking about is 2's complement, which is that we invert all the bits, but then we add 1. And this is going to give us a nice representation that Alex was just talking about, where our representations are divided such that if you go forwards counting, you get 1, 2, 3, 4, 5, 6, 7 up to the maximum value. And then as you go the other direction around the clock, you're going to get -1, -2, -3, -4, -5, -6, -7, and negative. I think there's actually an error here. That should be the largest positive number rather than the largest negative number is off by 1 from the largest positive number. It's 1 smaller, which is indeed one downside of using this representation. And then we can write that out with the bit patterns. So we have, starting at all zeros, we can go around the clock writing our bit patterns out. And so that's just a refresher, knowing that that's something you will need to know for the exam. Vincent?
What was the downside again for 2's complement?
A downside of 2's complement is that you're going to have 1 fewer negative number than you have positive numbers. Which takes us to one more thing that we're now able to do, now that we know our representation of numbers, is we're going to want to actually be able to manipulate individual bits within our number. And this is important if you're writing either software or hardware that is going to actually do something like storing floating point numbers. You need to know how to actually make those operations happen and what those operations would look like. So we're going to skip the hardware design. That's going to happen later on in your careers. But for now, we're going to look at least on the software side, how we manipulate individual bits in C. And this gives us to our last set of operators that we're actually going to use in C. And all of these work on a collection of bits at a time. So if you have a 32-bit integer and you use one of these operations, it's going to impact all 32 bits. But it's going to be applied on a bit-by-bit level rather than the entire number at once. So let's look at some examples of these. So the first operation is called shift left. So here we have a bunch of collections of 8-bit integers, and these are going to be our exemplars for using these operations. So shift left takes all the bits in the number and moves them one place to the left. Now, who can see a potential challenge with this? Tim, do you have a microphone?
What do you do when it gets to the end? Does it wrap around or what?
Yeah, so let's say we had a 1 in the leftmost place and we do a left shift of 1, that bit now has nowhere to go. So typically what we're going to do is not wrap that bit around, we'll just put a new 0 on the right-hand side and we will drop that bit from the representation. A shift right, likewise, does the same thing but reversed, moves all the bits one place to the right, but adds a 0 on the other side if you, as you're dropping bits out the front. So you'll notice how for our very first shift left example, the rightmost bit is now a 0. And what is shift left equivalent to doing, assuming that we don't have a 1 that we're dropping out the front? Danny, let's get you a microphone so you can say that a bit louder for everyone.
It is equivalent to multiplying by 2.
And how do we know that?
Because it's in base 2.
It's in base 2. So just like if we were to move a number, every digit in a number written in decimal up one place. So if you take the number 11 and you move the number 11, each of those digits up one place in the tens, in the ones, tens, hundreds, thousands column, it's the same thing as multiplying by 10. When you do it in base 2, it's the same thing as multiplying by 2. Likewise, shifting right is going to be, Danny, dividing by 2. So if you take the number 100 and you move that one digit that's in the hundreds place one space over, it's now in the tens place. It's like dividing by 10. Same thing happens in binary. Now, some operations for which there is less of a clear analog are these ones over here, the bitwise OR, the bitwise AND, the bitwise XOR, also known as exclusive OR, and bitwise NOT. And so the first 3 of these are going to be 2 number operators. So they're going to require not just one set of bits, but a second set of bits. And you can see underneath the bitwise OR, I've actually written a second number that we're going to perform our operation with. So these are called binary operators, not because they work in binary, but because they require two operands. So they require one number and another number. It's like addition is a binary operator because you have to add a number to some other number. So the way OR is going to work is it's going to look at each of the bits, and if either of the bits is a 1, the resulting bit in the same place is also going to be a 1. So as long as one of those bits is a 1, the result bit is a 1. So for the first one here, are either of those two a 1? Guys, are you awake? Are either of those two a 1?
No.
Okay, so we have a 0. Are either of those a 1? Yes. So we have a 1. Are either of those a 1? Yes. Okay, that's probably enough, and you can repeat the pattern throughout all of them. So that is a bitwise OR. Okay, bitwise AND is similar, except in this case, we're going to get a 1 in the result only if both A and B have a 1 in that place. So in this case, do both A and B have a 1? No. Thanks, Mal. Do both A and B have a 1? No. Do both A and B have a 1? No. Do both A and B have a 1? Yes. So that gives us our first one. And just repeat that process across the entire bit string. The next one is interesting, and there's no real analog in the normal mathematics that you would have seen thus far. This one is as long as this one is if one of them and only one of them is set to 1, then the result is 1. If they are both set to 0, get a 0, and if they are both set to 1, also get a 0. So what we're looking for here is a pattern where the top and the bottom are different. So in this case, if they're different, we're going to get a 1. So the first one, let's start from the far side again. Are they different? No. Are they different? Yes. Are they different? Yes. Are they different? No. And so on and so forth throughout the entire pattern. And this operation is actually at the heart of a lot of cryptography, which is, I think, pretty cool. And then the last one, a bitwise NOT. This one's very simple. It just flips all the bits. So it inverts all the bits. So where in the original you have a 0, change it to a 1. Where in the original you have a 1, set it to 0. And those are all of our bitwise operations. Danny, Tim, you've got a microphone.
With the bitwise NOT, is there like an arithmetical interpretation of if A was an integer?
It depends which integer representation you are using. If you're using 1's complement, it is the negative version of the integer. If you're using 2's complement, it is the negative version of the integer minus 1, I think. I think that's right. But again, these operations are expressly not designed to be arithmetically equivalent to some operation on an integer because they're agnostic to what integer representation you're using. We had another question. Vincent.
So for bitwise exclusive OR, hang on. Sorry, but could you please explain again?
Bitwise exclusive OR sets a bit to 1 if only one of A and B have a bit set to 1 in that place. If both of them have a bit set to 1, it will put a 0 in that place. And if both of them have a 0, it'll still be a 0. So it's kind of in the name, it's exclusive OR because it's the same as OR, but if both of them have done a 1, then it still sets it to 0. So it's exclusively one of them can be 1 for the result to be 1. And then just a reminder for how to do our 2's complement. So write the magnitude of the number, invert the bits, and then just add 1, and that'll get you to 2's complement. So now let's go back to our integer representations briefly and look at the 2 programs I promised I would show you earlier. And the computer already reset. But these are int bits and float bits that will allow us to see the actual representations of the numbers. I forgot to return to these earlier, which is why we're doing these now. Okay. So the way this program is going to work is it's going to take in, we're going to have an integer that we're going to look at the bit representation of, and the way we'll do that is by using our shift operations combined with the AND operation to look at one bit at a time effectively. So what this is going to do is it's going to take a number that is just a single one, just a 1 in binary, so 0001, and by shifting it over progressively, we're going to have a 1 in each different place within the number. So for the first time the loop runs, that'll just be a bunch of zeros and then a 1. If we shift that right one place, if we shift that left one place, then we'd get that number. If we shift it left 2 places, we get that number. We shift it left 3 places, etc., etc. And this is just multiplying by 2. So it's giving us 1, 2, 4, 8, 16, 32 progressively over the number. Now, when we've done that, what we're going to do is a bitwise AND operation. And remember, a bitwise AND operation is going to return a 1 if for every place in that number there is a bitwise AND is going to return, for a given place in a number, is going to return a 1 if there is a 1 in both A and B. Now we already know that in B, in this over here, there's only going to be a single 1, and each time the loop runs, that 1 is going to be in a different position. So if we run an AND, it will tell us for position 1, we know when the loop runs for the first time, there's a 1 in the first position in B. What we don't know is if there is a 1 in position A as well. If there is a 1 in position A as well, in the first iteration of the loop, the bitwise AND of both of them will return a 1. Okay, that's the first iteration. Now the second iteration, there is now a 1 on B only in the second position. So what we do is we calculate the bitwise AND, and now in the second position of A, if there is a 1, it's going to bitwise AND correctly with that 1 in the second position in B, and then we'll get a 1. However, if not, we'll get a 0 from that entire bitwise AND. So this is a process called masking. We're essentially moving a 1 all along and trying to see if at any of those positions, if there is going to be a 1 in that position in A. If there is a 1 in that position at A, what our program is going to do, it will print 1, otherwise it will print 0. This line here is just going to print a space after every 8 bits, just for us to be able to see it. And then we have one more step here, which is to calculate the loop bounds based on the size of an unsigned integer, just so this works no matter if our machine is 32 bits or 64 bits. So let's give us a run, and then we will go to Danny for a question. Let's start with 1. So we can see the number 1, the representation is just the 1. A 0 is all zeros. A 2 is like that. 3, and now let's try a random number-ish, and we can get the bit pattern out like that. So one other thing you'll notice is that for an even number, you're always going to have a 0 in the ones place, and for an odd number, you're always going to have a 1 in that place, because that is the ones place. And so by definition, an odd number is a number that has a 1 in the ones place, because it's not divisible by 2. Danny, you had a question still?
I figured it out. I was wondering why this wouldn't represent numbers backwards. It's because you started at that end and going down.
Yeah. And you can also use this to figure out the endianness of your machine. Okay, now we have the same thing, just for float bits. Only this time, because these bitwise operators only work on integers, we've got this strange line which is going to cast our floating point value, or our double value, into an integer but just so that we can, we're not trying to actually convert the number. We're not like taking 134.5 and trying to get 134. What we want is an integer that's using those same bits. So it makes no sense as an integer. It's not going to interpret if we were to print it out as an integer. What we're saying is we just want those same bits of memory that would have been used for the float, and now we're going to use integer operations on it bit by bit. And the reason that works is because when we're doing these bitwise operations, as Danny and I were talking about earlier, we don't actually care about how integers are represented. What we want to know is what is the specific bit pattern under there. So we take in the value, we cast it to an unsigned integer, and then we're going to do the exact same thing. So GCC And so you can see here we have the 0 from the sign bit. We then have our exponent with the bias, and then we have the mantissa represented. Any questions on those? Okay, we're pretty happy. Okay, so now I think we are at a good time for let's take a 6-minute break. Take us to 11:25, and I will see you all in a few minutes. Okay, and we're ready to come back, and I have kind of a fun question for all of you. Who has heard of the game Degrees of Separation? No? Okay, so the way that it works is let's pick a famous person, let's say Barack Obama, and you have to figure out how many links away you are from knowing Barack Obama. So from you to someone else would count as one link. So let's say I know Ray Ray, Ray Ray knows Michelle Obama, and Michelle Obama knows Barack Obama. That would be one link from me to Ray Ray, one link from Ray Ray to Michelle, and then one link from Michelle to Barack. And you can do this in all kinds of fun ways. So for example, you can count how many links away an actor is from having been in a movie with Kevin Bacon. This is called Degrees of Kevin Bacon. The reason people think it's fun is because he's been in a lot of movies, so it's very often that you can find a very short path from any two movie stars to Kevin Bacon. Now in the maths world, we also have degrees of separation from Paul Erdős, who is a famous mathematician. And he unfortunately had tragedy in the middle of his life when his wife passed away, and he became a meth addict and also a prolific collaborator, roughly at the same time. So what happened is he sold his house, he stopped renting, and lived out of a suitcase for the rest of his life, and he would be an itinerant mathematician, where he would go and sleep on people's couches for a couple days, collaborate with them, and then move to someone else's couch. And so in mathematics and in computer science, we have degrees of separation from Paul Erdős, which is how many papers you are away from having collaborated with him. So if I've collaborated with someone else and that person collaborated with Paul Erdős, then I would have an Erdős number of 2. Likewise, if we call the degrees of separation from Kevin Bacon a Bacon number. Now, who here knows Natalie Portman? She was Princess Amidala in Star Wars. Does anyone know a bit about what she did before she was in Star Wars? Or it might have been after. Tim? No, not in the movies. Outside of the movies. She studied physics and maths and actually published a paper in the field, which means that Natalie Portman has both been in a movie and had a paper in maths and physics and CS, so she has a Bacon number and an Erdős number. And by memory, I think her Bacon Erdős number, which is the sum of her Bacon number and her Erdős number, is I think a 5. By memory, I'll have to look this up. I can look it up very quickly now. Natalie Portman, Bacon Erdős number. And you can entertain yourself for hours. She has a Bacon Erdős number of 7. I was wrong. So there'll be some people with smaller. Now, here's a couple of fun facts about me. So I appeared on an episode of The Project with Christine Anu, who was in The Matrix Reloaded. Christine Anu appeared with Lawrence Fishburne in Mystic River. Christine Anu appeared with Lawrence Fishburne in The Matrix Reloaded, and Lawrence Fishburne appeared with Kevin Bacon in Mystic River. So that would be a Bacon number of 3 for me. And then I co-authored a maths paper with Nadia Henninger, who is my advisor, who collaborated with Pierre Gaudry, who co-authored with Peter Lawrence Montgomery, who co-authored with Paul Erdos 4. You add Bacon number 3 and Erdos number 4, and I'm practically Natalie Portman. That is in fact true. Not that I'm actually Natalie Portman, but the rest of it. Which kind of leaves us with a fun game that all of you can play. So we can't do, unfortunately, have any of you appeared in a movie yet or on IMDb? Yeah? Max?
I was on MasterChef.
And? Did you win?
Well, no, I was like an extra.
Oh.
Well, I mean, I was on it with Gordon Ramsay, so.
That's pretty cool. So you've probably got a finite Bacon number. I have the database somewhere. We can figure it out. I've got some code that you can run. So at least we've got someone with a Bacon number. Anyone published a paper yet? Probably a little early, but just in case.
You have to co-author it though.
Yeah, you have to co-author. It can't be a solo authored paper. Okay, not there yet. So life goals. Beat me and Natalie Portman for a Bacon Erdos number. Max already has an advantage on all of us, well, except for me yet. So instead what we'll do is number of degrees of separation from the king, from the current king of, well, I guess the king of Australia. So how many degrees of separation would you guess that you are from the king? Any individual of you. Okay, a 4 from Alex. 4 from Lottie. I not have you heard of, but like if you spoke to this person, they would know who you are. Let's make that. 5 for Gar.
I took the biggest negative number.
So Gar, you have a 5 because you know Lottie and Lottie's a 4? Okay.
I think someone here might be.
And I try and
Think someone here might be. So you think that someone here might be a 3?
It warns me that it'll overflow. Yeah.
You have to think about who I know.
Oh, Alex, do you think you're a 3?
Which implies there's more negative numbers.
Do you have an idea of... Okay, Alex is going to tell us how he's a 3.
It worked fine.
So I'm on a youth advisory board with my MP. It was before she got voted out in New Zealand. But she's definitely met the Prime Minister. And the Prime Minister, Jacinda Ardern, has possibly met the King or has definitely met the Governor General who has met the King.
So that gives you...
Either a 3 or a 4, I don't...
Which means everyone in this room is a maximum of...
5, yes.
Well, hopefully they're a maximum of 4 if you've actually got a 3, and if not, everyone has got a maximum of 5. So you can actually see how this works out relatively easily to get you access to even pretty famous people. So that is going to be our motivating question for the next little component of class, is figuring out how many degrees of separation between you and the king. And so I can show that for any of you in the room, it is a provable maximum of 4, not because this is true for any individual in the world, but I mean, we've got Alex, so we're practically kingly here, practically royalty. But we need an algorithm to be able to check, because it's not good to just go through everyone and ask them all the people they know and ask all the people they know, all the people that they know. We need some systematic way of doing this. So one way to do this would just be to try it practically, ask people around, but where we're all algorithmaticians now, so we can start to create a data structure that would actually help us with this problem. So let's build a tree. Okay, I've got some of you in the class. Hopefully all of you know each other now after having been here a little while. So Xia knows Mal over here, and Finn, who sometimes comes in and sits at the back over there. So this is the binary tree version of everyone's friends. What's the kind of sad thing about a binary tree for representing friendships? Jamun, so Alex, give him the microphone.
So unfortunately, you only get 2, assuming that friendships are both ways.
You only have 2 friends, and this doesn't look like people are friends both ways. So Angel is the friendliest person in here because all friendships stem from her. So this is probably not the best way to represent friendships. What would you recommend?
A graph.
Graph. Okay. So, well, one thing we can do is make the links bidirectional. So we can have, for every person who has a link outwards, they have a link inwards as well. So now Bowie and Xia are actually friends, which is nice instead of just being one way. But also we probably want to extend beyond just having every parent has 2 children, which is going to give us a much more complicated... Yeah. Well, we've got an energy drink over there, but unfortunately Finn wasn't even awake enough today to make it in for me to give him the energy drink. So we can also have links between people who are not directly related to each other. So in this case, we want Bowie to be able to be friends with Finn, even though they're in different places on our organization of nodes. Unfortunately, this is going to make a whole bunch of the algorithms that we used for exploring things in binary trees very, very difficult, because now we can potentially get into loops, because you can end up in a way where you get back to the path you came. We're not going to have any nice ordering property, because where is the beginning of this thing? I mean, I think you could maybe say that Angel is the beginning of this, because seems to have more links. But really, who in this room has more links than anyone else? So for the purposes of this graph, we are going to just assume that all our friendships are 2-sided, and I fortunately know almost all of you at this point, and so I will be the most popular. So all of you have a link to me, and let's count that as link number 1. And then I had a high school friend, Maddie, and she went on a date with Prince Harry. It was for a charity gala, so unfortunately they didn't get married, but Prince Harry knows the king, although I'm not sure they're on great terms. And so all of you are a provable 4 steps away. Now, we can do this because you can see up on the board how to do those steps. But if we're from the perspective of the computer and we're only looking at one node at a time, we need some algorithm that can also achieve the same thing. So we need to figure out algorithmically how to get the degrees of separation. Now, this material is largely going to be covered in your next year classes. So let's start with a formalism where we're going to call each of the people a vertex, V, like each of the nodes in what we're going to call a graph, and each of the links we're going to call an edge. So each of the nodes or each of the vertices are connected by edges. And so essentially we've got 2 primary techniques that we can use to try and solve our degrees of separation problem. So let's, on attempt number 1, try and go as deep down as possible through the collection of friends. So starting at Angel, I'm going to highlight each node as we go through it. And then when we look at a given node, we have a number of choices about which node to observe next. We could look at Bowie, at Aditi, at Lara, at Jamun, or at me. And so what this version is going to do, going deep, is what we call depth-first search, is it's going to pick one of these, let's say the first one in some list, and it's just going to keep going down that path. So let's pick Bowie, and now let's pick one of Bowie's friends, so Xia, and now let's pick one of Xia's friends, Finn, and now let's pick one of Finn's friends, energy drinks. Energy drink has no friends. So that's a dead end, so we're going to backtrack. So let's go back to Finn. Okay, from Finn we can go to Dr. Connie, high school friend Maddie, Prince Harry, and the king. Now, what we can do is we can keep track of how deep we had to go in order to get to the king eventually. But we ended up traveling through 7 edges, so that doesn't seem to have gotten us the shortest path to the king, although it did give us a connection to the king, but 7 degrees of separation was not what we're looking for. But we can be clever. What we can do instead is use a different data structure that we've already built up earlier in semester and use this to figure out how we do our exploration. When you get a node, put all of its children on the stack, or all of its neighbors on the stack, I should say. So a neighbor is any node that is connected to the given vertex. So we have the original node on the stack, then we have all of its neighbors, and then we pop, we're done, and now we pop one off the stack. Okay, we look at it and put all of its neighbors on the stack. And what we're going to be doing in this way is we are going to be sequentially going deep, because whatever is on the stack will have been a neighbor of the previous most deep node. And then if we get a dead end, well, we just throw that node away and then we keep going down the stack. So that gave us our algorithm from before that we could use to figure out how to chart that path. Our alternative, though, is to go broad. Instead of going down one of the neighbors and then going down its neighbors and then its neighbors' neighbors and then its neighbors' 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 neighbors, what we can instead do is figure out and look at all the nodes at a given distance away at a time. So let's start again with Angel, and all the neighbors that are all the nodes or all the vertices that are one step away. And so this is all of these highlighted nodes are one step away. So now we've looked at all the things one step away and confirmed that none of them are the king. Okay, so now what we're going to do is collect up all the things that are 2 steps away. Oh, no, sorry, I was correct there. So Angel, everything 1 step away is Bowie, Jamun, Aditi, Lara, and Dr. Connie. Now, everything that is 2 steps away, kind of messed this up a bit. So everything that's 2 steps away should be Aditi and Lara's friends, but Aditi and Lara are friends with Dr. Connie, so I'm still 1 step away. I've already been marked in a color. However, Skya is 2 steps away from Angel, and high school friend Maddie is 2 steps away as well. But now Prince Harry is 3 steps away, and we get to the king, which will be 4 steps away. Travel through 4 edges. So Angel to Dr. Connie, to high school friend Maddie, to Prince Harry, to the king. If I'd colored this correctly, we would have seen it for the rest of the graph, but you can still see it working. So the idea here is to put each vertex in a queue instead of a stack, and then repeatedly extract the front item. And when you extract the front item, put all of its neighbors in the queue. And so that is called breadth first search as opposed to depth first search. And really one way of viewing the difference between them is just which data structure you use in order to choose how you extract the children, how you extract the neighbors once you've put them in. So we can go from linked list, which is very restrictive, which had just like a one link one way or maybe a link backwards, to binary trees where you could have links to multiple directions to your left and to your right, and now to graphs where you can have links as many directions as you like and as many friends. Danny? No? You looked like you were ready to say something. Oh, you figured out your bacon number?
It's 4 if you count writing credits.
Oh, what do you have a writing credit in?
I wrote a video film with my friend. In that film, his mother, Nadine Garner, starred in it. Nadine Garner, the actress, has been in a film with Rado Michelle, who was in a film with Kevin Bacon.
So bacon 4. That's pretty awesome. Okay. So for anyone else, get back to us later in the lecture with your bacon number and we can talk about it. Okay. So, is there more? No? Okay. Vincent.
Bit of a somewhat silly question.
Yeah.
Is what is Bacon's bacon number?
0.
Okay.
If you are Bacon or Erdos, you are 0. You are the goat. The question is, what is Bacon's bacon Erdos number? So it would be really amazing if Kevin Bacon and Paul Erdos had started a movie and written a paper together. Unfortunately, Erdos is dead, so that's not going to happen. But
Posthumous publishing.
So that is actually happening. There are people who are still getting Bacon numbers of 1. Not Bacon numbers of 1, Aradosh numbers of 1, because he started work with a number of people who are still living. And when those people complete the work, if they complete it, they put his name on it. And so part of the reason to keep working on the problem that you once collaborated with him on is to reduce your Aradosh number. So it's a big fun badge in the maths community. Okay, so now we have our graphs, are at least conceptually what our graphs look like. And the same way that we had with trees and linked lists, after doing the conceptual work, we now need to figure out how to actually represent it inside a computer's memory. So what we could do is the same type of thing. We're having a node T or a vertex T. Let's stick with node T because that's what we've been using thus far in the class. But the question is, what do we put inside it? And this is going to be a bit of a question for us. So the question is, let's say you remember when we had our linked list, we had a next pointer. When we had a binary tree, we had a left pointer and a right pointer. How should we represent things in our graph? How do we structure, what is inside our struct for a graph?
I suppose like maybe an array of pointers.
So that's a really good idea. We could have an array of pointers. What's one challenge with having an array of pointers?
Well, an array which means there would be a limited amount of pointers.
So if we use an array, we'd have a fixed number of friends or connections or edges, unless what could we also do that we talked about a couple of weeks ago, if we had an array but we wanted to make a bigger array later?
We can reallocate the memory.
Yeah, so we could use arrays and dynamic memory. So that'd be one way of doing it. What would be another way of doing it?
We can use linked lists.
Yep, so you could have a linked list of all the edges of all the neighbors that someone is connected to. So that'd be another good way of doing it. So this would be the very naive way, is just set aside, instead of left child and right child, say neighbor 1, neighbor 2, neighbor 3, neighbor 4, neighbor 5. This is obviously not good because then you need to work with those variable names and that's going to give you very lengthy and very clunky code. So a better idea is what Gabriel suggested, which is that we can have either a linked list of nodes or an array of nodes of pointers to nodes stored at every other node, at every other vertex. So in this way, inside every node, so let's say we've got the Finn node, now that he's graced us with his presence. Where'd you go? At the back there. And what we can do is we can figure out all the other nodes that he's connected to. So if we have numbered our people from 0 to 12, then Finn has a link to 3, which is Xia, a link to 6, which is Mal, a link to 8, which is Energy Drink, and a link to 9, which was Dr. Connie. Now, what we've done here is also should be a little suggestive of another way that we can actually structure this without using the array of pointers stored at every location. What's another way we could represent the structure that's based on the way this looks? Gabriel, you've still got the microphone. We want to represent the edges between people, so who is friends with who?
I suppose that's distance.
So distance wouldn't capture all the information. I guess you could say let's use distance for every node, say how far away from you that person is. That could be one. That's getting close, but let's give it to Sam.
Maybe a two-dimensional array or like a two-dimensional maybe linked list, I guess, if you can do that. So we can matrix it at least.
Okay, a matrix, that's a great idea, and we'll return to that in a second. Let's just hear Darcy's suggestion before we...
You could use either an adjacency list or an adjacency matrix.
Okay, that's cheating, but yes. If you already know the answer, this is no fun. So let's go with Sam's idea, which was to turn this kind of thing into a matrix that represents who is friends with who. So right now, this is showing that for each person, give them a slot in the array for each person that they're connected to. But we could flip this on its head a little bit and do something that looks more like this. So put a 1 if two people in the matrix where two people are friends, or equivalently where there is an edge connecting them. So if we look at row number 7, Finn over here, and we look at energy drink over there, we see there is a 1, so Finn and energy drink are friends. And then we can fill this out with 0s and 1s to get the entire picture of representation of our graph in a slightly different format.
With that matrix with the 1s and the 0s, would that matrix always be like symmetrical along like the diagonal?
Yeah, so it'll always be symmetrical along the diagonal in this case because an edge from A to B implies an edge from B to A. So this is where friendship is reciprocal. However, if we're going back to our old model where you can be friends with someone and they aren't friends with you, then it won't necessarily be symmetrical because the edges will be directional. And that's what we call a directed graph. We can think about how long it will take to go through a person's friends. So let's say we have n people in the class and we are using the linked list version of storing their neighbors. What is the worst case time to iterate through someone's friends? O of n, because they can have at most n friends. So let's say that we are going through each person and we are trying to look through their, and we are not revisiting any person. What is the worst case time it would take us to go through the entire graph, starting with a root, assuming that there is a way to make your way through the graph to everyone so that all the nodes are connected? What is the worst case time to traverse the entire graph using depth first search, where we're using these linked lists as our representation? And who's got a microphone?
Would it just be O of n, worst case? Like if it's just, like if the graph is just a stick?
So the problem is we can end up with links that are going from each of those nodes. Let's say you're correct about there being a single path to get to all of those nodes, but if all of those nodes have friends and we don't have neighbors and we don't know who those neighbors are, then we might have to check those as well. Bowie has got her hand up, so let's pass it back to her for a second.
Would it be n to the n?
Why n to the n?
It's like it might have n people in the entire list and each person has n friends. And it will take n to the n for searching the entire space.
So let's try and add this up. So for person number 1, they have potentially n friends, right? Potentially n links coming out of them. Then the next person has potentially n friends, so that's n plus n plus n plus n plus n, n times. Is that n to the n? That n to the power of n? No. What is that? That's n squared.
Okay.
Right? Because you're adding n possible times. So it's not multiplying, it's not multiplicative, it's additive in this case. Because for each person, there are n possible places you can go, but you don't actually go down that path because you've seen that person before. Let's say that there is a straight line right through to visiting all n nodes. Now that you've visited all n nodes, let's try and investigate all the edges, because each time we were only following one edge to get through each people in a straight line. Each of those edges end up being dead ends. So even though at each step there are n possible edges to look at, Once we get to that step, we don't go down further again because we're just returning to someone we've already visited. That makes sense? Getting there. We can do a drawing of it. We have more questions. Garv. Let's get a microphone to Garv.
So doesn't that make the big O time for DFS O of n plus m? If you can explore a maximum of like, all the other nodes and then maximum of all the other edges, that's the time complexity?
Yeah. So that's where we were getting to next.
Okay.
So what we're going to get is we're actually, the right way to calculate this is to figure out how many edges there are and how many nodes there are altogether. Now, in the worst case, that could be n squared, but the right way to actually represent it is going to be in terms of the number of edges there are in the place, because that tells us how many different paths to go down and how many different nodes to go down. And that is actually going to be a much better bound for us, which is going to apply to both breadth first search and depth first search, which is that if you count up the number of possible nodes to visit and the number of edges to visit, the way you figure out how much work it's going to take you is such that you're only going down every path once. And then if you've already been down a path or you've already visited a node, mark it as visited, and that is going to allow you to not revisit it again and not redo the work. Okay, so what we had before looked like a big matrix, and so this is what we're going to call the matrix representation. And this is going to give us, unfortunately, an O of n squared runtime to look at all the to calculate the paths, because now we have an n by n matrix, and we're going to have to look, if the matrix has dimension for the number of vertices, the number of different people in the class, and in this case, we're going to get a v squared or n squared if n is the number of people runtime, and that's because we're going to have to look at every entry in the matrix at least once in order to determine what it's set to. The advantage that we had before when we were using the linked list representation was when we got to the end of the linked list, so if someone only had one friend, we wouldn't have to go any further along because the end of the linked list is the end of the linked list. However, in the matrix representation, you have to keep checking along each of the entries for that person in order to actually determine if they have an additional marking as being a friend with someone else. Any more questions at this point? Okay. So that is essentially all of the core algorithmic content for the class, which is quite exciting. But that leaves us with a bit of a struggle. It is week 11, and we've still got 4 hours left. So we've got a couple of things planned. So we're going to talk a little bit about strategies for problem solving and trying to sum up some of the class and how each of the different types of things we've learned fit into broader paradigms for solving problems out there in the world or solving even theoretical problems and algorithms. And we do have a planned industry guest next week from Quantium, which is a consulting company that does a lot of engineering and data consulting. And the person we're having come in is a graduate of FOA, and she has a very exciting story, particularly for those of you who do not think you'll do as well in FOA as you might hope. There will be probably some wise words from someone who might have been in a similar situation once upon a time. So we've got a couple of possible things that we can do now. Option 1 is to take everything we've learned in the semester and try and categorize it, synthesize it, and come up with some big takeaways. So we could take all our algorithms and categorize them by maybe the type of problem that they're designed to solve. We could talk a bit about complexity, and we've spoken a little bit about complexity already with big O. So we could categorize algorithms by like all the big O of n algorithms, all the big O of n squared algorithms, etc., etc. And we might do a little more of this. And we could also talk about the techniques that you use to design a given algorithm, which is another way of categorizing them. So let's start with categorizing by problem type. So I did a fun thing last year, whenever it was, when I made this particular slide. And I looked up the great list of algorithms on Wikipedia. And there is a long list, and it's kind of fun just to skim down this, see how many you know, how many are just extensions of what you know. And we could actually take a look at a whole bunch of different types of problems in the real world and try and match them to the sort of algorithmic approach that might be appropriate for them. So determining optimal train routes, modeling animal behaviors, filling in holes in damaged photos, all different problems that we might have in the real world, we can then try and mix and match them to the big Wikipedia list of algorithms. And so for a given type of real world problem, a different class of algorithm might be useful, or it might actually turn out that multiple different classes of algorithms end up being useful for a given problem. We could also think about different design techniques that we've already learned this semester. So we've talked about a divide and conquer a little bit. We haven't yet talked about so much about these other categories. So that's where we'll do a little more work now to talk about some of those other categories of algorithmic design techniques that we might choose to use. So let's start with generate and test. A really good example of this category that we haven't spoken about explicitly in class, but that's been there implicitly, is generating and testing. And one example of this that we've done is the finding primes problem. So when we had our, who here remembers find primes from earlier in semester? You would have seen it in a bunch of different places. The core algorithmic idea there was generate a number, test if it's a prime. If not a prime, generate the next possible number. Is it a prime? If not, keep going. And this is an approach that is valid in some instances. There are a number of possible real-world problems that this might be useful for, but there are also some significant limitations. Let's get a microphone to Alex. Okay, so what are some limitations of the generate and test approach? Why might it be a frustrating approach to use in many circumstances?
Well, like you have to like trial and error basically like every single permutation, like until you find whatever you're looking for.
And what are some improvements that we might make? What about our problem would suggest that might be a good candidate for generate and test?
Well, I think prime is a pretty decent like problem that you can solve with generate and test. I'm not aware of any other cleverer way of.
So with the primes, there's actually a whole interesting world about like what is an efficient way to find primes. With the primes, it works, but one thing that we aren't factoring in is that we actually know quite a lot about primes. There's still a lot of great mysteries about them, but we certainly have techniques such that we can do a better job of generate and test than what we were doing in class. However, we also know that primes are unpredictable, and so generate and test is a good applicable approach if we can figure out the right generation and test strategy there. So what we're going to be looking for is something where a more analytical approach won't work, but where we can actually get an advantage over just pure random guessing, because pure random guessing is a fairly poor algorithmic approach most of the time. Is there another comment on that from someone? No? Okay. An example of a poor approach to generate and test is trying to get the works of Shakespeare from monkeys typing on a typewriter. Probably not going to happen anytime soon. So one approach that you might use generate and test for is subset sum, also known as the backpack problem. So if any of you are a frequent overpacker and have a large backpack, this is a real world problem that you might have actually experienced, and frustration in packing a backpack or packing a shopping bag actually is indicative of the computational hardness in this instance. So the ideal formulation of this problem is you have a backpack that contain items up to a certain weight, and then you have a bunch of items, each of a certain weight. What is the closest that you can get to maximizing how full your backpack is? So let's say you have a laptop that weighs 3 kilos, a lunch that weighs half a kilo, and then 6 books, each of which weigh different amounts. What is the optimal packing of your bag such that you can get the most stuff in it and leave the least weight behind out of your items? And this is an example where generate and test might actually work. So let's see if I can get us an implementation of it for us to look at. So let's clear off our terminal. Here's another example of our algorithmic approach of generate and test. So here what we are doing is we are iterating through possible packings of our bag. Every time you have an item, there are only two possible states that the item can be in. Either it's included in the final packing of the bag, or it's not included in the final packing of the bag. And so in generating every possible combination of items that goes in the bag, for each item, investigate the world where it's in the bag and look at all the other possible items, or choose the world where it's not in the bag and then also look at all the possible items. And so this leads naturally to a recursive formulation. The recursive formulation is here. So if there is no weight left in the bag, if you've perfectly packed the bag, return success. If you have perfectly packed the bag, return success. So in this case, we're using a slightly modified version of the problem. We'll talk a bit more about that in a second. So what we're doing here is we are reducing the number of items to be packed by 1, and we are, in this case, living in the world where the available weight to pack has been reduced by that item because that item is in. And in this world, we are not including the item, but still excluding it from future consideration. And that's really all there is to it. For each item, go down the recursive path where you've included it, go down the recursive path where you haven't included it, see if either of those works out. So in this version of the problem, instead of trying to get as close to the best possible weight as to the maximum packing as possible, there is another version of subset sum where instead we say, is there a set of items that you can pack to get the backpack exactly full? And this is something we'll talk about in a minute, which is the difference between the optimization version of the problem and the decision version of the problem. So the decision version of the problem is there a packing that gets you exactly to the precise weight that your backpack can hold? And the optimization one is, what is the best you can do? And these are closely related and indeed opens up a whole world of algorithms, which is like, let's say that you want to pack it exactly full, but you can't. How close to optimal can you get? And yeah, I'll talk a bit more about approximation algorithms as well a bit later. So just to go back down here one more time. Over here, if the item is included, subtract from the available weight in the backpack, the weight of the particular item, and then in the next iteration, only consider the remaining items in the array. So this is the equivalent to reducing the size of the array by 1, is we're now not including that last element in the array. In this world, we haven't made any modification to the weight because we haven't included the item. However, we still want to exclude the item from further consideration. And that's how this one works. And then just to reiterate here, this base case is when you have exactly packed the backpack such that there is exactly 0 weight left in it. So that's our backpack problem. And now there is another problem that you could imagine doing generate and test for, where you can apply a similar approach. And hopefully all of you have seen a Sudoku before, and we're going to revisit this next week as well. The goal here is it's a tabletop game that people use to amuse themselves when they don't have anything better to do, when they don't have foundations of algorithms assignments to finish. And the goal here is to find a set of numbers such that in every grid of 9, there are the numbers 1 to 9. In every horizontal, in every row, there are the numbers 1 to 9. And in every column, there are the numbers 1 to 9. So it's a 9 by 9 grid with 9 possibilities for each cell. So how many possible fillings starting from a blank grid are there? Knowing that in real Sudoku, some of these are filled. Ethan? Only 81 possible. There are 81 squares. So 81 squares, each with 9 possibilities, which, how would you compute that?
Well, 9 to the 81, or about 2 times 10 to the 77.
So that is an awfully large number. Now there are also a bunch of like beautiful research papers on solving Sudoku. And so this one is called There is no 16 clue Sudoku. And so the question here is, what is the minimum number of clues that you need in a Sudoku such that you can analytically solve the rest optimally? And so this is proving that you need at least 17 clues for a solvable Sudoku. So a big question here is, can we shrink the number of solutions that we have to check in some intelligent way such that we can then reduce, rather than generating from the total possible boards, to a more intelligent set of boards based on the clues, based on the things filled, and based on what we're doing so far. So we have a few possible solutions we can use to try and get a winning Sudoku board. So one strategy would be to iteratively fill the board, and when we get to something that violates the terms of the Sudoku, we backtrack. So this is equivalent to try and fill it out, and then as soon as you notice a mistake, cancel, don't go any further down that route from that version that had the mistake, and then keep filling in other numbers. And this solution actually works relatively well. And so this is the pseudocode for doing that to Sudoku. So figure out the next space in the grid that doesn't have a number in it, and then if there are no such spaces, great, you're done. Otherwise, for every number in numbers 1 to 9, set the location that's unfilled to that number, check if it's invalid at that point. If it's invalid, immediately move to the next possible filling. Otherwise, do this recursively. So just, you've tried, say, filling in the number 1. If the number 1 makes it invalid, no point checking further versions of the board that have a number 1 in that place. Now try it with a number 2. If a number 2 doesn't create an invalid grid, run this whole procedure again, picking all the unassigned spaces that result from filling out that board with the number 2 in that position, and then just do this recursively. And in this way, you're actually able to reduce the combinatorial explosion that you'd get from trying every possible Sudoku board. So this is much, much more intelligent. But when you solve a Sudoku, what process do you use typically? This is for anyone in here who's done one before. Just give me a description. Mal, you've already spoken today. Anyone else? Someone who hasn't said something today. Mal, these puzzles, what do you do?
Look at the board, see like where the numbers are, and then on the X and the Y axis. And I also look at the grid to see if which numbers are in a grid. And then based off that, I'll see if any numbers are guaranteed to be that can be put in a square. And that just saves a lot of time.
So tell me more about that. What do you mean guaranteed to be in a square? What does it mean for a number to be guaranteed to be in a square?
Well, we know, it's been a while since I played Sudoku, but we know that, like say you have 3 rows, if there's like say a 9 on the left one, at the top left, and then there's a 9 on the right side of the row that's on the middle, then we know that on the bottom that there's a guaranteed 9 in the middle somewhere.
So a simpler example might be, let's say we have a row that's already filled out with the numbers 1 to 8, and there's one blank space left. We can make a logical inference that there's only one possible number that can go in there, because by the rules of the game, all the numbers 1 to 9 must be represented. So that clue, this is admittedly a very easy clue that it's given us, is that the only number that can fit there is the number 9. But we can also do logical deductions on other types of clues, so we can put things together. So if it has numbers 1 to 7, and then we look at in the row, but we look at the column for that for the blank squares, and one of those columns has a 7 in it, we know that the 7 can't be at that row and that column at that top in that missing square. It must be the next one over. Let's say we have a row, and the only numbers that are missing are the numbers 8 and 9. And there are 2 squares. One of them must have an 8, one of them must have a 9. And then in one of those columns, there is already an 8 just in a different row. What that means is in our original row, we can't put an 8 in that same column as that column already has an 8 there, which means that that one must be the one that has the 9 and the other column must have the 8. And we call these constraints. And this means essentially that there are additional logical rules that we have imposed on the placement of the numbers, and we can use logical reasoning and inference in order to go from the clues that we've got to the possible set of fillings of the grid that we might have. And this is a type of programming called constraint satisfaction and inference. And this is actually really cool. I've used this practically for a real-world problem most recently, but you can also do it for something like Sudoku. And another way of writing constraint satisfaction is just with this term SAT. That's how computer scientists often write about it. So you can write that Sudoku is essentially a SAT problem. If you were to write the constraints appropriately, you could formulate Sudoku as one of these constraint satisfaction problems and also write it in a typical form that computer scientists write these called CNF, which stands for conjunctive normal form. So let's actually try and write out some of these constraints and write out some of the variables. So the way we no longer actually teach a class on constraint programming at Melbourne Uni, I think. So this is the main time you'll get some insight into it, which I think is kind of cool. So let's say that for every possible grid space, we create a variable. But even more than that, instead of just for every grid space, let's have a variable for every grid space. Let's have 9 variables. So for grid space 0, 0, let's have variables S000 to 009. We have a grid space. This is grid space 0, 0. It can take on a range of values, and there are 9 possible values, which means if we want 9 variables, so we have 001 to 009, just to make that a little more intuitive for you. So space 009, that variable is set to 1 because there is indeed a 9 in that corner. So corner 0, the variable where a 9 is in there is set to 1, which also implies that 008 is 0, 007 is 0, 006 is 0, 005 is 0, 004 is 0, 003 is 0, 002 is 0, and 001 is 0. And because I'm one indexing these, there is no 000. Sorry about that confusion. Now, that is the full set of variables for the top left square. Okay, now let's look at the square next along. That is square 01. And because there is an 8 in there, that means 018 is set to 1. What that also means is that 017 is 0, 016 is 0, 015 is 0, 014 is 0. You get the point. And we have one more space in this grid filled, and this is square 22, and it has a 6 in it, which means S22 is set to 1, which also means that 225, 224, 223, 222, 221, 227, 228, 229 are also all set to 0. And so now we have a set of variables that represents every square and every setting in our 3x3 grid. Now, of course, we can extend this to the full 9x9 grid, but let's stick with our 3x3 for the minute. So now let's write it out in logical form. So now I've written out all the variable settings for all of these values. So you can see 001 is 0, 002 is 0, etc., etc. And this triangle, known as a wedge symbol, means AND. So it is the case that this is true, and this is true, and this is true. All of them are true simultaneously. So this is what we call the starting assignment for our problem. It is the set of settings for the variables that we know to be true at the beginning. What we want to know is what should the variable settings for all of these be such that some set of constraints that determines what a correct Sudoku puzzle is are all true and not violated. So questions at this point? You're not expected to be able to replicate this.
So you're saying the final exam won't be us having to write down a on-paper algorithm to solve a Sudoku in a general case?
I mean, the algorithm that you use to solve this is also complicated, not just the equations. There are two parts of this, writing the constraints and then writing a solver for the constraints. And you won't have to do either of those things. Garv has a question. Let's get him a microphone.
So there are ones like it's like 1 and like 227 and 1 and like 019, but there are no values like if we look at the cell 22, that's not a 7. So is there a reason that the 227 is ANDed with the 1?
227 is 0.
Oh, sorry. So 226 is equal to...
Yeah, 226 is equal to 1, 227 is equal to 0. Okay. So we also know some other facts about our grid. We know for square 0, 2, so it's 0, 2, that square in the corner there, it must be the case that one of these is true. Otherwise, that grid space does not have a number in it. So one of these variables must be set to 1. So either it's a 1, or it's a 2, or it's a 3, or it's a 4, or it's a 5, or it's a 6, or it's a 7, or it's an 8, or it's a 9. One of those must be set to 1. And so we have an additional constraint that we can write. One of these must be set to 1. And that symbol, the upside down wedge, is an OR symbol. So it must be the case that for our Sudoku to be solved, one of these must be set to 1. So far, this is just, I haven't said exclusive yet. So far, I've said one of them must be set to 1. I haven't said that only one must be set to 1. We know that because we know how Sudoku works, but we haven't written that constraint out yet. So we're going to need to write a lot of constraints to get all our equation is going to get really, really big if we want all the rules for a Sudoku to be covered. Now, these symbols are kind of like you've seen the summation symbol, like the big sigma. So that means add up for all of these items, put a plus sign between them. This is the same kind of thing, except this is put an and sign between all of them, or put an or sign between all of them. And we need a lot of constraints. So this one says that there is at least one number in every cell. So this is the OR that we saw before. For every row, for every column, for every possible value setting, put an OR between each of those values. So for every cell, that cell must be 1, or it must be 2, or it must be 3, or it must be 4, or it must be 5, or it must be 6, or it must be 7, or it must be 8, or it must be 9. That's this one. This one says for every column, for every number that is possible that we want to appear in that column, and for every 2 rows, for every combination of rows, it has to be that it can't be the rows can have no 2 rows can have the same value if they're in the same column. Now, I'm not going to go through the logic for each of these constraints and try and explain them one by one. If you want, you can sit down and puzzle out through them yourself, because it does take a lot of time to go through them, and it's also not a requirement for the class that you actually understand how each of these constraints works, but I would encourage you to do it just for your own edification. Do it once. Okay, so that's some of our constraints. And then there are more constraints still to actually put the Sudoku together. And this constraint says that each number appears at most once in each 3x3 grid. And this is a little bit of a complicated one because we need to account for how to represent the 3x3 grids. And you would hope that we're done. Unfortunately, we're not done. We still need more constraints. At most one number in each cell, each number at least once in each row, each number at least once in each column. And then finally, at least each number 0 to 9 has to appear in the 3x3 grid. So has anyone been keeping track of how many clauses? 10 clauses altogether? well, this is 10 expressions, each of which generates clauses. So let's go back to just the simple one. So this generates 9 by 9 by 9 clauses. So what is 81 by 9? That's 729 clauses just from the first term, just from the first one of these. And so if we sum them all up and figure out how many clauses we get, anyone have a guess? 1 billion is way too many. 5,000 you said, Sam? Remind me your name again, I'm sorry. Alex, that was it. You're the third Alex. Alex, and Alex. So we add them all up, we get 11,988 clauses in this particular formulation. Now there are a bunch of different ways that you could write these. 11,988 clauses is hard. And this is still hard to solve, but not just in a way that is difficult for a human to do. It's fundamentally hard. We can prove that this algorithm sits in a class of problems, all of which are very hard in the same way. And we can learn things about their big O time by grouping them together. And in our final week, we're going to actually look at what that means to be in a class of hard problems. So now I generated this program this morning with ChatGPT, so there is a major asterisk warning around it. But I only thought this morning, how cool would it be if I actually had a program that generated these clauses and solved them? So we will take a look at that on this computer, I think. And this one is written in Python because writing the clauses out in C would be a little painful. ChatGPT could probably still do it for. I'm using O3. There is a sample puzzle, and you can see in practice, it actually solves it really quickly. So even while the big O runtime of this algorithm may be really difficult, in practical instantiations, it might actually be relatively fast to run. So let's look at the code for this. And again, I'm not expecting you to understand the code. It's more for a little bit of enjoyment, if that's the kind of thing you enjoy, which I do. So the main thing going on here is adding all the different constraints that we need. So itertools.product is a way in Python of generating lots of different combinations of things. And so for each of the different blocks, we're adding various different constraints. You can see here, if you take a look, you'll remember on the slides I had for each of the 3x3 grids, there was like the +3 to figure out the correct grid squares that it was going to apply to. So we're doing that there. And the program actually ends up being relatively short overall. So what we're actually doing in our program is we're having the program automatically write the various different terms in the equation for us. And then separately, I'm calling out to a library which has a built-in algorithm to actually run the inference process. So once you've written out all the constraints, there are a bunch of algorithms out there that take the set of constraints and attempt to actually run them. So let's talk about some of the limitations of generate and test quickly. So generate and test is not going to be useful when the solution space is too big, when it's unclear how to generate a possible solution, or when the solution space is hard to explore in a way that makes sense to get you closer to the solution. Checking potential solutions might also be slow compared to constructing the correct one, which is kind of what we did with our Sudoku problem. We figured out ways that we could get closer to constructing it rather than just generating different ones. And with that, let's leave it for today. I hope you had some fun. Actually, well, one more thing. So this is something that I'm personally very excited about. One problem that we have in the department, in like the School of Computing Systems, is we have a list of 110 subjects. a list of 110-ish academics, and the academics all have the preferences of what they want to teach in a given semester. And what we could do is we could actually formulate this as a constraint problem. So we could add the constraint that for every subject, for every possible instructor, the variable must be set to 0 if the instructor hasn't put that as a preference in their preference list. And so actually the way I'm in charge of doing this allocation this year, actually the way that I've done the allocations, the department might hate me when I show them the results, but actually the way that I did this was I wrote out something like 20,000 constraints using one of these programs that include everything like how much time has someone has available, what their preferences were, when they wanted to teach, etc. And I ran that through one of these solvers, and in a couple of seconds I can actually get a really, really, really good matching of instructors to subjects. Now, we can have a discussion later if you want to talk to me about it, about some questions around optimality of that. But it was, in my mind, a really, really cool use of constraint programming. So these things are useful in practice and probably saved me hundreds of hours in trying to manually figure out how to balance these different preferences, because I can't in my head figure out the right way to satisfy all the constraints simultaneously. And with that, we are done for today. Thank you very much, and I will see you all for our very last week soon.